Okay. So, last time we discussed what differential forms were, and the exterior derivative, the definition. So today the goal is to talk a little bit more about the exterior derivative, and then discuss cohomology and why cohomology gets us what we want it to get us. Then talk a little bit about manifolds, and then probably state and maybe prove, if we have time, the Mayer-Vietoris theorem, which is our first theorem that allows us to do computations.
Last time you went from the definition of, no, you went from section to the definition of exterior derivative, and you said going the other directions, like.
Yeah. Oh, I'll sketch a proof of Stokes' theorem.
Okay, awesome, thank you.
I won't go through it's like, you can check the book bottom too if you want more details, but yeah, I'll sketch a proof of that. Thanks for asking.
Thank you.
So just to review, we discussed what this thing was, which is essentially something in linear algebra where you feed in k different vectors and Rn, and it'll give you some notion of a k-dimensional volume. And the conditions were that it should be alternating in the sense that if you switch any two of the entries, it should get negative sign, and it should be bilinear. And these were like related to the geometric properties of having working correctly under the scaling condition, where you scale any one of the vectors, and having invariance of the area under shearing. And then after that, so this is what a general differential form looks like. Some functions, so w omega I should say, depending on your coordinate x, times these guys, and as a reminder, this is a multi-index. So if I is equal to like 1, 2, 3, then this is dx1, dx2, dx3. And dx is like an infinitesimal one of these guys attached to every point. And then, motivated by Stokes' theorem, we came up with this definition of the exterior derivative. So recall that Stokes' theorem, which we wanted to hold, was this statement, because we used it a lot last week. And based on this, we got this formula, and the idea was, again, let's say you want to like integrate omega over a cube. Then what's going to happen is if you apply this formula, you're going to get contributions from each of the boundary. On the left side, you get d omega over the cube, and on the right side, you get omega over each of the boundary faces. And then, for example, you get a contribution from the bottom of the top face, which will be like xy and xy. So that'll be I is equal to x and y. And then you're differentiating in the z direction, and so you take a derivative with respect to z. And it essentially ends up giving you this formula at the end. Any questions on any of that last week? Okay, so let's see that this gets us first what we wanted it to. So let's look at what d is from omega 0 to omega 1. So remember, omega 0 is just functions, and omega 1 is co-vector fields, if you want to call it that. It's something where at every point you feed in a vector, and that gives you a number. So what this is saying is, let's say you take some function f, then you'll get df, which should tell you, give me a vector v, and df evaluated at v will tell me how much f is changing in that direction. So if we compute this out using this formula, then what we get is, for example, in R2, or let's work with R3. In R3, we'll get partial f, partial x dx, plus partial f, partial y dy, plus partial f, partial z dz. Great. And so that looks a lot like the gradient, and df of v is, for example, partial f, partial x times the x component of v, and similar for y and z. So it does give you like the notion that you expect. This is some sort of a derivative, which says if you move in this direction, this is how much the function is changing. In higher dimensions, it's not quite a derivative. There is something that will give you a derivative called Cartan's magic formula, which I considered talking about, but I think it would just take us too far aside. But let's look at what d does from omega 1 to omega 2. So a general one form, right, is going to look like f, which is f1 dx plus f2 dy plus f3 dz. Right? So what should df do? So the first thing we do is we take derivatives of this guy with respect to each of the different things. So we have partial f1 partial x dx plus partial f1 partial y dy plus partial by dx because you have a dx out here. And then you have terms for the other ones. So first, I guess I'll ask the question, can we sort of ignore one of these terms? Yeah.
The dx wedge dx.
Why?
Because when you take two differential forms, because you can think it's like anti-symmetric. So if you switch over, it has to be this negative, so it has to be zero.
Yeah. So dx wedge dx. I guess I didn't talk about this too much, but these wedge products also like satisfy the sort of alternating and bilinear property within like these d terms itself. So this will be equal to negative dx dx, where you just swap these two, and so then because it's equal to its negative, it should equal to 0. So what that means is that we can ignore this first guy, and if we add the other terms, then we can ignore the derivative of this with respect to y, and what we'll end up with is partial f2 partial x dx dy plus partial f2 partial y dz dy, and then partial f3, we can ignore the z derivative of this, so partial x dx dz plus partial f3 partial z partial y dy dz. Okay, any terms over here which we can combine? Yeah.
The dz dy dy dz.
Okay. So tell me what that should be. Something times what? So what should go in the parentheses?
df3 dy minus df2 dy.
What's a DC?
Oh, dc. Yeah, not bad.
And then the outside?
dy dz.
Dy.
Thank you.
Yeah, so can you explain why the negative sign comes about?
Because you switch over to the dz dy.
Yeah, so if you swap these two, then you're going to get a negative sign over here. And similarly, you can combine this dy dx, you can swap the two and make it into dx dy. And then what you get is partial f2 partial x minus partial f1 partial y, which, remember, maybe I should write this like in terms of x, y, and z. So this is x, x, y, y, z, z. So this will be the derivative of the y component with respect to x minus the derivative of the x component with respect to y. And then the third term would be dx dz, where you have to swap this one, so you get a negative sign here. And it's the derivative of z with respect to x minus the derivative of x with respect to z. So hopefully this looks familiar. This is the curl, so we did indeed recover that as well. And finally, let's look at three forms, or two forms to three forms. So if you go from omega 2 to omega 3, then a general thing will look like this. Dx dz plus f3, I think this should be z dx, and f3 dy dz. Okay? So if we take this out, right? So we have to first do like derivative of f1 with respect to x plus derivative of f1 with respect to y, derivative of f1 with respect to z. And then we get dx and dy and a dz term here. So which ones do we really need to keep? We get something dx plus something dy plus something dz times dx dy. Which ones can we ignore? Which ones do we need to keep? This is the derivatives of the first one. Yeah.
We can ignore the dx and dy.
Yeah. And we just keep this guy, right? So what that ends up being is partial f1 partial z dz dx dy. What should the next term be here?
Partial f2 partial y dy dz dx.
And the third one?
Partial f3 partial dx. Partial x 2x dy dx. Dy dz, sorry.
Yes.
And now, instead of naming it like this, I will name it like x, y, z. this is x, y, and z. Okay, so we want all these to be the same. So what do we need to do with this guy to make it into dx, dy, dz?
You do like 2 transpositions.
Right, so you have to move the z over once and then move it over again. So that's 2 transpositions, and that'll give you a negative sign twice, and so you don't change anything. And then here you have to move this to the middle and then swap around these 2. So again, that's 2 transpositions. So that gives you 2 negative signs. And what we end up with is the sum of these 3, dx, dy, dz. So we have recovered the gradient, curl which I've erased, and the divergence all in one formula, which is what we want to do. Yeah.
Is there, because earlier we were saying that we're going to like order these with like we did like E1, E2, E3, we always ordered our wedge products with the lowest index first.
Sure.
And here dz comes first to make the divergence have the right sign on the component. Is there like a convention for like when you enumerate the basis vectors on the alternating space, like which one you should use?
Yeah, so every single time I write this out, I feel like I mess it up. So the nice thing is, no, but the thing is, right, I mean, like, there's no canonical choice because there's no canonical basis,
Okay.
right? So, but the nice thing is that, like, this expression doesn't really care, because if you accidentally said, like, dx, dz, then in effect what you're doing is just multiplying the function by -1.
Right, yeah.
So if you're, like, choosing a different order, then you're just choosing a different, like, different functions to represent your differential form. But the differential form itself stays the same thing. It just, the differential form, the way I like to think of it is like, at every point, it eats in k vectors, it gives you a number. And that description is sort of like, doesn't matter like how you write it out, like that's like an object, right?
Yeah, that makes sense, thank you.
Okay, cool. So you asked about Stokes' theorem, so let's sketch a proof. And the proof is actually really stupid. So essentially, here's how it works. I won't really go into the details. If you want the details, you can read Block 2. It's in the first chapter. So if you have a manifold like this, so usually I guess you learn about manifolds and you're like, oh, you cover with open charts, right? But then how do you work on the boundary? So in this case, like the open charts are UI, and the UI goes into Rn, and this is some homeomorphism into a subset of Rn. But you can't do that at the boundary, right? So at the boundary, what you do is you take some open chart, and so in this case, let's call this Vi. So this Vi is going to embed into Hn, where what is Hn? This is equal to the set of points x1 through xn, such that xn is greater than or equal to 0. So it's the upper half point. And what this does is it's gonna be some homeomorphism, so the boundary gets sent to this line over here. So what you do is, have you guys seen partitions of unity before? Okay, so partition of unity, just as a reminder, is a set of functions phi I, such that the support of phi I is contained inside ui. We'll see these later today as well. And the sum of phi I at every point is equal to 1. So these are essentially like bump functions at every point, such that if you add them all together, you get 1. So when you want to compute an integral of omega in general, what you do is you take an open cover, and you take the sum over all your indices of the integral of omega over this open cover ui times the partition of unity. And so the point is that the sum of the partition of unity just gives you 1, so this isn't really doing anything. It's over some manifold. But what this does is it makes this guy locally computable by these homeomorphisms. And I'll talk about like fallbacks and stuff a bit later. I don't want to talk about that right now. Later today, probably. So what you do is, in the case where you're embedding it into Rn, let's say you take the integral of some d omega times phi I over Rn, right? And this case, what you're doing is, this is going to be some function which has compact support and like sort of vanishes outside of that, right? And you're integrating this guy. So this will look like a bunch of things, which will be like integral of partial omega I by partial x1, dx1 up to dxn, plus a bunch of other things that look like this, right? So what you do is you're integrating this over Rn. So you first integrate the x1 coordinate, and this integral becomes the integral over Rn minus 1 of omega I dx2 to dxn. Oh, I got the partition. Phi I. Oh. So essentially, like maybe you have to do integration by parts or something like that. But you end up with some omega times something, which may be something else other than your initial partition unity. The point is that this guy has compact support, and you're integrating this from minus infinity to infinity, and because it has compact support, this gives 0. Right? Does that make sense, or was that a bit too sketchy?
Wait, why does compact support mean the integral is 0?
So this phi I prime has compact support. So when you integrate this guy, right? Maybe you have to do maybe the point is that you do an integration by parts and you transfer the derivative over to here.
Sure.
So then what happens is you have.
This is the derivative of phi.
Yeah, I think this should.
Oh,
be the
yeah,
derivative.
I believe. Okay.
I think there's already this one.
Yeah, okay.
And then. Yeah, you get something that has, I don't remember the details, but you have something which has compact support, and when you integrate, you have to evaluate on the endpoints, right?
Yep.
And since you're integrating over x1, x1 is over the entire real line, but then because the thing has compact support, it vanishes at the boundaries.
Yep.
And so it ends up giving a contribution of 0.
Like this is when you integration of parts, you get an integral in boundary terms, and the boundary terms vanish because it's compact support.
Right, the boundary terms vanish.
And then this integral vanishes because the derivative of the function is just 0 everywhere.
Yeah.
The,
Okay, I forgot to bring the book with me, but yes. The point, I don't remember the exact data, but the point is that you have like something which vanishes away,
yeah.
and then you have compact support, and you just do that. And in the other case, what happens is I think you might actually, instead of taking this guy, you might actually take the integral d of this guy, and then you show that if you take the sum, okay, so this is what you do. You actually take the whole thing under the d, and so the point is that d omega, I guess I haven't shown this, but you can show that d omega times phi is equal to d omega times phi plus omega d phi. So it satisfies some sort of product rule. And if you take the sum over I of these guys, right? The point is that d of the sum of phi I is just equal to d of 1, which is 0. So if you take the sum of all of this, then this guy doesn't contribute anything, you still end up with the integral of d omega. So here what you do is you take the derivative of this whole guy, and now when you take, now you integrate with respect to x1, and now you get omega times your partition of unity, and the partition of unity goes to 0 at infinity, and that's why.
So yeah, that makes sense.
Yeah.
So it's in the bottommost integral. There's no derivative on the phi.
Not in this one, no.
Yes.
But on this one there is.
And the derivative goes away because you integrate it.
Because you integrate over x1, yeah. And you also end up with like something derivative with respect to x2, and you do that same thing, but you integrate the x2 direction.
Yeah, makes sense.
And then in the upper half plane, it's the same exact thing, except now when you're doing this integral over r n minus 1 of omega phi I, now instead of evaluating dx2 to dxn, instead of evaluating it from, or I guess in this convention, 1 to n minus 1, instead of evaluating it from negative infinity to infinity, you evaluate it from 0 to infinity, right? And the point is that the infinity thing still vanishes, and the thing at 0 gives you just omega. So this is in effect, there's a mega sign here. There's probably some mega sign that shows up somewhere, so I'm just gonna put that in there. And then this ends up giving you the sum or the integral of these Rn minus 1 guys of omega times phi I, dx1 to n minus 1. And so this is integrating over all your boundary hyperplanes of omega, and then once you take the sum over phi I, then you're just getting the integral of omega over the boundary of your manifold. Does that make sense?
Because the boundary gets mapped to the x or the
To xn equals 0.
Yeah.
So I think it's kind of like once you build up the machine, it's kind of dumb, right? You do like integration by parts, and you're like, oh, it has compact support, so it goes to 0 over there, or you're just evaluating it at 0. But yeah, that's the proof of Stokes theorem sketch. Questions? That was really sketchy. If you want more details, read the book. It's like 2 paragraphs. Yeah.
When you okay, so actually I don't know what my question is.
It was 2 paragraphs, when you just write out the paragraphs for us.
Wait, how do you go from on the right side, the top integral, or like the integral in the middle of the board to the integral below it?
Because you're taking like the sum over I of these guys. Yeah, I'm not writing out everything because I don't want to write out everything.
Okay, sure.
It's like okay, so here's what happens, right? The integral of omega over the integral of m of d omega
Yeah.
is equal to the sum over I of the integral over ui of d omega phi I.
And that vanishes.
This vanishes on the ones where it goes in the interior.
Yeah.
For
so
the ones where it goes
uses-
on the boundary,
Yeah.
what you get is the sum over I of the integral over the boundary of, I guess I'll call these ones vi for the ones that are on the boundary, of omega times phi I, right? Times like this n minus 1 dimensional measure. And then this is equal to the integral or the boundary of m of omega, because again, the sum of the partition of unity is 1. So essentially, like split up into pieces.
Yeah.
Anything on the interior doesn't matter. Anything on the boundary gives you a boundary component, and then you get that.
Yeah, makes sense.
Okay. Cool. Any other questions? In that case, yeah, let's define cohomology. Okay, so HK is defined to be the kernel of D over the image D. And so what this means is this is D as going from omega k to omega k plus 1. And this is D going from omega k minus 1 to omega k. And so this is analogous to what we've seen before, where if you have something where the curl of G is equal to 0, then G is equal to some gradient plus the sum of lambda I fi, where each of these also satisfy curl of fi is equal to 0. And we saw that these guys each detected a hole, and this guy's the gradient. So what we're doing is we're looking at everything which satisfies this equation, and we're sort of ignoring this piece and only focusing on these functions. And the point is that the kernel of D is a linear map between these 2 vector spaces, so this is also a vector space. And you're quotienting out by this vector space. And this crucially uses the fact that D composed with D is equal to 0, so that this image lies in this kernel. Can anyone give me a highbrow explanation as to why this is true? Yeah.
Is it just like when you take the other derivative, you can switch the order, because Schwarz's theorem and the differential forms cancel out?
Yeah, so if you compute it out, that's what happens, which is like you get two, you get a dxdj, dxj, dxi, and then you get a dxi, dxj. But the derivatives are the same either way, so those 2 terms cancel out when you flip the sign. The geometric reason for this being true is that, again, you have Stokes' theorem, integral over omega d omega is equal to the integral over the boundary of omega, right? So if you put a squared, then this will be a d omega, and so this will be integral of the boundary of omega. But the boundary of the boundary is always an empty set. So this is the geometric reason why this is true. Questions on that? Okay. And so I claim that this detects holes. So let's discuss that a bit. So what's the point of these two things? Let me make some definitions. So I'm going to call a CK equals to the set of k dimensional submanifolds of M, where this is CK of M. Right, so for example, C1 might be, one element could be like this path, one element could be this union of paths, and C2, for example, you could have a sphere, you could have a torus with a boundary part like a disk removed, etc., etc. Does that make sense? And you can take like disjoint unions of things and whatnot. And then I'm gonna define C upper K of M to be functions which take functions which assign to every k-dimensional submanifold a real number. Okay? And so the reason for this is that let's say that we have in omega inside omega k of M, then this induces a map which I'll call phi sub omega inside ck of M. And so what this is phi omega evaluated on some manifold S, some submanifold of M is equal to the integral over S of omega. So the reason I'm writing it like this is because I guess usually you like think about the surface being fixed, and you're sort of integrating something over some fixed surface. But I instead want to think about like, okay, I'm going to keep the differential form fixed, and think about integrating different submanifolds, integrating this differential form over different submanifolds. Okay, so in this context, Stokes' theorem says that phi of d omega evaluated on some surface is just phi of omega evaluated on the boundary of that surface, right? So what this is saying is that if I want to evaluate this function on some manifold like this, all I care about is the boundary parts. So if I have another manifold which has the same exact boundary, then phi of d omega evaluated on these two guys is going to give you the same number, right? Because they have the same boundary, and this only depends on the boundary of this guy. So this is what it means. If we call this like omega prime, then this is what it means for omega prime to be inside the image of D. That is to say that this, these are called the spaces of chains, which is why it's denoted by C, and this is the space of cochains. So this is saying that this cochain depends only on the boundary of the manifold that you're evaluating it on. Okay? So what does it mean for now omega to be inside the kernel of D? So this means that if you take phi so let's say that you have V inside CK. So this is some k-dimensional submanifold such that there exists a V prime, so that V is the boundary of V prime, right? So what this says is that if we evaluate phi omega on V, then this is phi omega evaluated on the boundary of V prime, which is phi d omega evaluated on v prime, which is integral over v prime d omega. But because omega is inside the kernel of v, this is equal to 0, so this is equal to the integral of v prime of 0, which is 0. So it says that if you evaluate this cochain on anything which is a boundary, you're gonna end up getting 0. Good? So what does this mean practically? Let's say that k is equal to 1. So let's say that you're evaluating something on a circle, right? And let's say that we go from this circle, we deform it a little bit into this wiggly circle, right? So if we like sort of stretch it out like this, then what happens is we can sort of follow the deformation that we took to get a submanifold which is in annulus, right? So what happens now is, let's call this part V1, let's call this part V2. Then phi omega on V1 minus phi omega on V2. Well, V1 minus V2 means like applying the opposite orientation to V2. I guess I'm being kind of loose with orientations, we'll probably talk more about it later. This is equal to phi omega of this annulus, right, which is equal to 0. So that means is that phi evaluated on these two submanifolds gives you the same number. So if you have two submanifolds which share a boundary, for example this guy, then you'll end up with the same number. Another example is, let's say you have this, where this is V1, V2, and V3. So this belonging to the kernel of D means that phi omega of V1 is equal to phi omega of V2 plus phi omega of V3, assuming the orientations work out. So the reason that this is sort of important is that a priori, the space of cochains is like horrendous because it's any function which goes from a chain to the real numbers. So if you take like this circle, and if you take like the same circle with a little blip in it, then a priori it could evaluate to like 1 on this circle and like 10 million on this other circle, right? So what this says is sort of, if you have nearby manifolds, they evaluate to the same number, and if you have some more complicated picture like this, then it also evaluates to the same number. Does that make sense? And this is sort of like the sort of stuff that we did when we proved like path independence, when we were trying to take a primitive of something with curl equal to 0, we need to show path independence, and this was basically the argument that we used, right? Okay, so the argument was like, if the curl is 0, then we expect it to be the gradient of something. So in general, why should that be true? So I'll write it over here. We don't need some more. So let's say that you have, so what we have is like, if this condition is true, we expect that the phi omega evaluated on some manifold should only depend on its boundary. So again, let's take like k equals 1, and let's take two paths, let's call it V1 and V2, which share the same boundary, right? So what we expect is that phi of omega of V1 is equal to phi of omega of V2. And why should we expect this? Because again, like if we can fill this in, then similar to what we did over here, the difference should be 0, and so these two evaluate to the same thing. And so now it should be reminding you of what we did last week. If these two are not the same thing, then that means that we indeed could not fill this in. There's some hole in our space which is preventing us from filling in the disk. So what this shows is that if you have something which is in the kernel of D, but does not come from the image, which means that you can have two manifolds with the same boundary such that the evaluation is different, then you have detected a hole in your space. Similar picture, maybe, which might be more illustrative, is like if you have something like this, and you have these two cylinders which share these two circles as boundary, then you might expect that phi omega value on these two should be the same. But if they aren't, then that means you have detected some like toroidal hole in your space, or some circular hole in your space, or something which doesn't allow you to fill in the torus. Any questions on this? Yeah.
I understand the kernel side of this work, but can you go over the image side again? The case where, where omega prime is in the image of the.
Yeah, so this says that, so this is then just Stokes' theorem. So this is d omega, and so this is saying that the integral over s of d omega is equal to the integral of the boundary of s of omega, which means that if we call this guy omega prime, if omega prime is equal to the d of something, then that means that if we don't know this a priori, then this is the integral of omega prime, right? So this says that
it's like Stokes' theorem in reverse, where it's like you're given omega and you suppose that's the d applied to some other differential form.
yeah, you're given omega prime, and you suppose that's d applied to this guy. But like even without knowing what this guy actually is, you know that this guy won't matter except for the boundary. Or that this guy only depends on the boundary. The rest of the shape doesn't matter because there is some omega.
Yeah, because on the inside there is some omega, and on that side is where like you have problems.
So you're integrating d omega over the cylinder.
Yep.
And so you're integrating omega over the boundary,
Yes.
right? But all I'm saying is like,
Oh,
technically,
you don't care what omega is because it doesn't matter because the only non-zero part of the integral is the boundary term.
Yeah.
Okay.
Yeah. So I mean, like, yes, this is kind of pedantic, but all I'm telling you is like omega prime is in the image.
Yeah.
I'm not telling you what it is the image of.
Okay.
But like even if you don't know what it is the image of, you can still make the statement that it doesn't matter what the interior of it is. So as long as you have two things that share the same boundary, that's integrating whatever the omega is on the boundary, and so.
Yeah, that makes sense. Thank you.
Other questions? Cool. So we have generalized everything that we have done in the first problem to like arbitrary dimensions. I think it's around 45, so that's like half across the. So I'll very quickly. I think maybe I'll be able to state Mayer-Vietoris. I don't know if I'll be able to prove it today, but the problem set this week is going to be computing things with Mayer-Vietoris, for which, I mean, you don't need the proof. It helps if you, I think Mayer-Vietoris is something that like everyone learning algebraic topology for the first time is like, it's hard because you've never seen exact sequences before probably, and then you have to get used to them. So you don't have to know the proof, but I think it's nice to see the proof. So I'll talk about that if I get the chance today, otherwise next week, but the problem session this week is going to be doing computations. Okay, so yeah, manifolds. So I told you how you can discover holes in subsets of Rn, but there are more interesting shapes. For example, a torus. And you're like, a torus has holes. Can we use the same sort of thing to discuss holes on a torus or on a higher dimensional shape or something? And the idea here is that if this is M, then if you have some embedding of M into some Rn, then we can define omega k of M to be sort of omega k of Rn restricted to M. And so that means is that you have some k form on the ambient space, but you're only evaluating it on k-unit vectors of M, right? So all you care about is the k form at some point of M, and moreover, you can only evaluate it on vectors that are tangent to M. So you can't evaluate it on the vector that's normal to M because that's not intrinsic to M, so you don't actually care. So I guess I said it in words, but does it make sense how one could define differential forms in this way? So one example is like d theta, right? So you can embed the circle in R2, and you can have d theta, which is like x dy minus y dx, and only evaluate it on these tangent vectors. And that gives you this notion of d theta. However, this is a bit annoying because you have to say that in order to actually do any sort of computations, you have to embed your manifold into some higher dimensional space. actually doesn't matter what higher-dimensional space you embed it into. So it'd be nice to have some sort of intrinsic formulation of this where you can talk about things just in the manifold. So how could you do that? Well, the idea is that C infinity of M, right, is smooth functions on M, which says that to every point you assign a number. So how you can describe C infinity of M is, let's say that this is your space, and you split it up into a bunch of open sets UI, right? So what you can do is you can say C infinity of M is equal to, is some subset of C infinity, the direct sum of C infinity of UI of the open cover, because every function on M gives you a function on each open subset of M, such that if you have, let's say that Fi is on UI, then Fi restricted to UI intersect Uj is equal to Fj restricted to UI intersect Uj. Right? So this just says that if you have two different functions here that agree on their intersections, so you can sort of piece them together to get a function on your whole space. So we're going to use the same sort of idea to define omega km in sort of an intrinsic fashion, where you're going to define differential forms on each open set such that they piece together nicely. So how do you do that? On differential math, where you want to differentiate things, and in order to do that, what you do is on each open set, you define a homeomorphism of UI into some subset of Rn, where this is the dimension of your manifold M, right? And now we know how to describe differential forms on Rn, so we know how to define omega k of phi I of ui, right? Because this is some subset of Rn, and then we just have k forms of that. And so some element of this will look like a sum of omega I dxi. Okay? And basically all omega k of M is a subset of the sum of omega k ui, such that these k forms agree on intersections. And again, like a k form, you should think of it like at one point you can feed in k vectors that will give you some number, and so this is just saying that that's sort of like a generalized function, and so this is saying that the generalized functions agree at every point. So the question is, what does it mean for things to agree? And for this, we're gonna need to talk about like pullbacks and whatnot. So what happens is like in one set, so let's see. So you have two sets, ui and uj, and so this gets mapped to something in R2, for example. This gets mapped to something else in R2, and then let's say that this intersection part gets mapped to this guy, and over here gets mapped to this guy. So when we're talking about functions, we just want to say that the value of the function at this point is equal to the value of the function at this point, the corresponding point. But over here, we have to say something stronger, because like you input not only a function, but also a vector. And so you have to say that this, the function value at this point with this vector input is the same thing as the function at this point with the associated vector input. So what is the associated vector input? Well, what happens is to go from this guy to this guy, you apply Pj composed with Vi inverse, right? So you go from here to here, over to here. And so this is just some function from R2 to R2. And so over here you can take the Jacobian, which will give you a map from this vector space to this vector space. Or sort of a more geometric way to talk about it is a tangent vector is sort of a little bit of a movement in some direction. So you can look at what this function is on this point and little points like the offset, and look at what the images of those 2 points are, and the difference of those 2 points gives you the image vector over here. So then if you have some map F from, let's just be general over here, like N to then you're given some vector v inside tangent space at the point at x in n. You can, it's usually determined t f of v, but I'm gonna note it as f of v. And so this lives inside t f of x m. So you have some point in the domain, you have some point in the image, and you can transfer function vectors from here to here. And again, the idea is just like look at a nearby point and look at where that gets into, and then the difference there will be your image vector. And so we're going to define this thing, which we'll call f star omega. So this is going to be a pullback, and this is going to be, so this is something that'll eat in k different vectors, right? So v1 through vk, and this is by definition omega of f of v1 through f of vk. So I haven't told you what omega is, I guess. Omega is something which lives in omega k of the image thing, and you're pulling that back to something in the base thing, or your original one. And so the reason for that is, this is, if you look at the case where k equals 0, then all this is saying is f star g of x is equal to g of f of x. So anything which is like a function on the image can be pulled back to something which is like a function of the domain. And anything which is sort of geometric on the domain, like a vector, can be sort of moved forward to something in the image, like we did over here. Are there questions on what conceptually we're doing here? So we're saying that you're evaluating k vectors over here. You have some form over here, which you want to evaluate on k vectors over here. So look at what the images of those k vectors are and evaluate over there. So that's one way to view it, or another way to view it is you can like pull back your differential form to this guy and then evaluate the vectors over here. That's how we define it. Questions? So then this condition gets replaced with the condition that if we call this guy phi ij, then phi ij star of omega j is equal to omega I, and you restrict it to ui intersection uj. So what you're saying is that you have a bunch of differential forms, and the way that you're comparing them on this intersection is by looking at the pullback of the transition functions, and those should agree with each other. And if they do, then you can sort of piece them together. And again, what this is saying is that you can piece them together into something which on M says at every point, give me k vectors and I'll give you a number. And this is well defined regardless of which open chart we choose because of this compatibility condition. Questions on that? So I guess I'll show you the formula for what this pullback is. It should be what you expect it to be. So let's say you have a map from Rn to Rm, which looks like f1 of x all the way up to fm of x, right? So then what is f star omega going to be? So omega is something which lives inside omega k of m, right? Or sorry, Rm here. This will look like omega I dxi. And so the pullback over here is going to look like the sum of omega I dfi, where dfi is, okay, so df, for example, 2, 3 is equal to d of 2, d of 3, and this is the exterior derivative applied to this single function, right? So this is nothing but like a change of variables formula, or the chain rule, or whatever you want to call it. So I'll give you two examples which should illustrate what's going on. So let's say that we have the two form dx dy on R2. And let's say that we take a map from the strip R cross 0 to 2 pi to R2, which is polar coordinates. Okay? So this is R theta. And so what happens is you have the coordinate functions are cosine theta, are sine theta, and so dx is just what you have seen it to be in multivariable calculus, what you hopefully should have somewhat of a vague intuition for. And dy is dr sine theta plus r cosine theta theta. Any questions on this? Okay, and then if you do dx dy, then what's going to happen? Well, you're going to have some terms which involve a dr, some terms which involve a d theta, d theta. Those you can ignore, right? So what you'll have is like this guy times this guy, and so you can ignore the terms of like common dx, dr, d theta, d theta, and so all you'll have is the cross terms left. And when you look at the cross terms, what you get is r cosine squared theta dr d theta minus r sine squared theta d theta dr, and you can swap these two to make this dr d theta, and then what you get is a plus sign over here, and this goes r cosine squared plus r sine squared, so you get r dr theta, which you probably learned in high school is how to compute areas in polar coordinates. So this is probably stuff that you've seen before, and what we've like formalized everything of like change of variables, Jacobians, and all of that. And another place where you've seen this is like physics. So vector fields very often aren't actually vector fields, they're very often actually one forms. So for example, if you have the electric field, then what it actually is dx plus dy plus dc. When people say that the electric field is a vector field, they're very slightly lying to you. It should be rather thought as one form. And let's say that you have gamma as a path from 0, 1 to R3, which is like gamma 1, gamma 2, gamma 3, and a dependent variable we'll call t, right? So what does the pullback look like? Well, it's what you probably expect, dx partial gamma 1 partial t dt plus dy partial gamma 2 partial t dt, and so on. So again, like we've recovered a line integral using this language of differential forms. This is what gamma star of e is. And so when we're talking about like integration, what you're actually, one way to think about it is like the integral over the image of gamma of e is equal to the integral from 0 to 1 of gamma star of e. This is sort of like the formal expression that you see. This is explicitly how to calculate it. And usually just sort of write out this expression, but we can see that this is sort of an example of pulling back this guy to the interval and then integrating this over the interval. And so earlier I was talking about Stokes' theorem, and I said that you look at open charts. What you're actually doing is you have a map from a homeomorphism from some subset of Rn into your manifold, and so you're pulling back your differential form of your manifold into that subset of Rn and integrating it over there. Questions? Do pullbacks make sense? So it's sort of like it's kind of cool. It's a simultaneous generalization of like Jacobians and line integrals and any sort of change of coordinates formula that you have in multivariable calculus all at once. Okay, so hopefully you get the sense that from the definition, in order to actually specify any differential form on a manifold is like horrendous, because you have to first off find an open cover, and then you have to like give trivializations, make sure that they agree on intersections, and it's just bad. So I feel like in practice, you sort of like work on things at a very high level and a very like sort of like a level at which like a differential form is something where you feed in k vector and it gives you a number. And then the only times you have to do computations is like over a sphere or Rn or something like that. and you sort of like make a bunch of equivalences between things and then boil it down to those cases where you have an explicit computation that you can do, and then you do that computation, then you're happy. That's, I think, how most of this class is going to be. But, yeah, so that being said, the way that you would, like, for example, compute HK plus a manifold is not by actually writing out differential forms and checking which ones are 0 and which ones are in the image of these. It's sort of a more formal computational method to do this. So, what's the idea here? So the idea is like, if you have some big manifold M, and let's say that we want to figure out the topology of M, but we don't know what it is. But let's say that we can split off M into two pieces. This left-hand side I'll call M1, and this right-hand side I'll call M2. So two open sets such that M is equal to the union of M1 and M2, right? So sort of intuitively, maybe you can say like, let's say we work on the circle, right? And let's say that we work on like this left semicircle plus something, and this right semicircle plus something. You should maybe get the sense that if you know the holes of M1, and if you know the holes of M2, and if you know how M1 and M2 sort of stick together, then you should be able to piece together that information to give you the holes of M, right? And so in order to do that, there's a theorem called Mayer-Vietoris. Actually, I'll do it over here. And this theorem essentially says that if you have such a decomposition of M into two submanifolds, M1 and M2, then you can piece together what the holes on these are in order to figure out what the holes on M are. Okay? And in order to talk about that, we are going to talk about some algebraic things called exact sequences. Okay. Who has seen exact sequences? Cool, you all have seen it. But just in case, I'll just do a really quick review. An exact sequence is a sequence of vector spaces, let's say like A1, A2, A3, and some other stuff, along with some maps between these guys, F1, F2, F3, and so on, such that the composition of any two consecutive maps is always 0. So F2 composed with F1 is equal to 0, and the image of F1 is equal to the kernel of F2. So I guess you all have seen this before, so this should be fine, but I'll give some examples just to clarify. So we usually denote the 0 vector space by 0. So let's say that we have this sequence. What does this sequence say in words? Yeah. Eric.
Okay, well, we know the image of the 0 map into A1 is 0, and so the kernel of the other one is 0, so the map from A1 to A2 is injected.
Yeah, so the image over here, the image of the 0 vector space has to be the 0 vector space. The image of A1 is the kernel of this map going to A2. So this says that A1 is a subvector space of A2. Similarly, let's say that we have this guy. What does this say?
The map from A1 to A2 is rejected.
Yeah, so in this case, the image of this map is 0. Sorry.
Yeah.
Yeah, so the image of this map is 0, so the kernel of this map is everything. And so the kernel of this guy has to be the image of the previous one. And because the kernel is everything, everything in A2 has to be hit by something in A1. And so that means that A1 to A2 is surjective. Okay, what does this mean? Yeah, it's a bijection. So this part of the sequence tells you that this is injective. This part of the sequence tells you this is surjective. So you combine the two pieces of information and you get that there's a bijection. What does this mean?
Injective, surjective. Like A1 into A2 is injective, and A2 into A3 is surjective.
Yep, so this is injective, this is surjective. But there's something else that you can say. So use exactness at this point to show that this map is surjective. Use exactness at this point to show that this map is injective. What about exactness at this point?
A3 is A2 on A1.
Yeah, so this is that the image of A2, which in this case is all of A3, is, sorry, the kernel of this map is exactly the image of this, but because this is an injection, this says that the image of A2 mod, the image of A2 is equal to A2 mod A1. Because the image of this is the kernel of this, so this says that whatever you have outside is this modulo the image of the previous guy, but the previous guy is injective, so you have that. And because this is surjective, you have this with A2. So this says that A3 is the quotient A2 mod A1. Okay. So take it, you all have seen such things before. And so what the Mayer-Vietoris sequence says is that if you have such a decomposition, then what you're gonna have is an exact sequence of vector spaces where it starts off as a 0 of m going to h0 of m1 directs on h0 of m2, going to h0 of m1 intersection m2, and then here you have some map which says goes to h1 of m, h1 of m1 plus h1 of m2 goes to h1 of their intersection, and then this goes to h2, and so on and so forth. So this says that if you understand the cohomology of m1, understand the cohomology of m2, and you understand how they interact with the cohomology of the intersection, then you understand the cohomology of m. And so I just drew a bunch of arrows, but I should specify what these maps are. So what happens is you have some inclusions. So you have I1 from M1 to M, I2 from M2 to M, and then you have J1 from M1 intersection M2 to M1, and J2 from M1 intersection M2 to M2. And these maps are I1 star, I2 star, and then this one is J1 star minus J2 star, and then this one is some map which we call delta, which is called the connecting homomorphism. Okay, so what is this saying? This is saying that you have some K form over here, which represents some cohomology class. So, okay, what is a cohomology class? A cohomology class is an equivalence class of K forms which satisfy the property D of that is 0. So you have some equivalence class over here. Let's choose some representative, omega. So this says that restrict omega to M1 and restrict omega to M2, and sort of keep track of those two pieces of information set. This one says, again, restrict further. So let's say now you have two differential forms, tau and eta. So this says restrict tau to the intersection, restrict eta to the intersection, and take your difference. And so what it means for this to be exact is exactly saying that, like, if you have two things, tau and eta over here, such that the difference of their restrictions to this is 0, then what that means is that the pullbacks agree on the intersection. And so what that means is that you can piece together tau and eta to get a differential form on M. So this says that if you have two things which agree on intersections, then you can piece it together to get something on the full manifold, which is sort of like how we define differential forms on our manifolds, right? And then this boundary map is a bit more Is the actual time like 7:15?
8:15?
Sorry, 8:15, yeah. Yeah, so does this make sense? I guess, yeah. I sort of have an explanation as to what the connecting homomorphism is, but I'll sort of explain that in the context of the proof. I don't think you actually need to know what it is for any of the problems that I'm going to give you. But you should be able to like work with these maps and the problems that I give you. So I think I might postpone the proof to next week. Do you have a question?
All the rows are exact as well.
Yeah, so all the rows are exact, and like this map is exact, the whole thing is exact. So that 0 to A, B, C to 0 thing, that's called short exact sequence. This whole mess, if this whole thing is exact, then this is called a long exact sequence.
Are you gonna prove the snake lemma?
Yes.
You should also prove spectral sequences.
No. Okay. Since we have 15 minutes, I don't want to discuss the proof. So instead, one of the problems that I give you is to compute the cohomology of complex projective space. And so one of my goals for this class is like, if you like all throughout high school, right? You learn algebra, and then more algebra. They're like, oh, we're gonna teach you calculus, but we're actually gonna make you memorize a bunch of algebraic formulas to do the calculus. So we're just doing more algebra. And then never do we actually get to do any geometry. So I wanna, in addition to teaching you like cohomology differential forms, try and like show you some nice things in like geometry, which people care about. Yeah.
Isn't the whole point of this to turn geometry into algebra?
Yes and no. It's to use like the algebra to understand the geometry. So one of the things that I think is like a topologist best practice, like projective spaces, these things show up like everywhere, and so I think it's kind of a sin to not know about it. So I'm going to talk a little bit about projective space. Okay, so I'm like winging this here because I did not write notes on this, but let's see how this goes. So I'll talk about first R, P, N, right? So let's talk about RP2. So let's say we have two lines in the plane. How many points do these two lines intersect at? One, usually, unless they're parallel, right? So one thing that you can imagine is like what happens if you take two lines and you sort of make them more and more parallel. So if you look at the point of intersection, like let's say that we draw a bunch of these lines which sort of become more and more parallel, then the point of intersection over here goes further and further away. So it's almost like the intersection is like going off infinitely far away. So what projective space does is it sort of adds in these points at infinity into your space. So in projective space, we have, for example, the statement that the intersection of any two lines gives you a point. And so we'll be able to like prove this over complex projective space using cohomology. And that'll give us some nice proofs of, for example, Bézout's theorem. So what does Bézout's theorem say? It says that if you have a degree D polynomial and you have a degree E polynomial, then, for example, this is a degree 2 and a degree 3 polynomial. So generically what's going to happen is that these are going to intersect at 6 different points. It turns out this will always be true, as long as the curves intersect transversely, whatever that means. And you work in complex space. And the reason for that is like, let's say we move this third line away, and then we still have two intersections until we have like one intersection over here, and then the intersections just disappear. So what happens there is the two intersections sort of like went into complex space. And over here, what could happen is like, as you deform your picture, the intersections move further and further away, and they sort of end up at infinity. And so the correct solution is to work in complex projective space, and then you have Bézout's theorem, which says that if you take a degree D and a degree E polynomial, then the number of points of intersection will be dE many times. And so we'll prove this in generalizations using cohomology, but in order to do that, I think you should have some hopefully somewhat intuitive understanding of what projective space actually is. So the way I like, there's like 3 different ways that I can give a projective space. So the formal definition is you work in 1 dimension up, and what happens is I like to imagine that there's some little guy standing at the origin, and you're like sort of looking up at the ceiling, and what happens is the ceiling is a copy of R2, right? And so every point in R2 is uniquely represented by a line that goes through the origin, and so you can represent R2 as sort of being the lines of vision through the origin where you are. But if I were to put a sticker like over here in 3-dimensional space, you wouldn't be able to distinguish that from a sticker put in the plane. So what you should do is you should identify points at their scalar multiples of each other because they look the same to you, and you sort of get a copy of R2. So the definition is RP2 is defined as R3 minus 0 modulo scaling. So the scaling condition is that A, B, C is equivalent at any scalar multiple where lambda is non-zero. So the reason we exclude lambda equals 0 and the 0 point is because otherwise everything would be equivalent to 0 because, yeah. And what you can sort of see is like, if you're sort of looking up, and then you look down and down and down and down and down until you're looking like perfectly horizontally, and then what ends up happening is you end up at a point where you're no longer looking at the plane z, I'll go to z equals 1, right? So you're no longer looking at the plane z equals 1, but if you trace the point that you're looking at, it's sort of the same picture that they veer off further and further away until they sort of end off infinitely far away. But then what happens is like if you look far enough in the other direction, then you're looking at exactly the antipodal point. And so what ends up happening is you sort of have this circle of points which is infinitely far away, but you have to remember to identify 2 opposite points. And the reason for that is sort of like, again, if you look at our picture of lines, where you have one line, and sort of like move this line further and further away so that the intersection moves away until they become parallel. And if you keep rotating it, the intersection sort of comes back from the other side, right? So you sort of have like infinity over there, which is like the same infinity over there. So sort of to exaggerate this picture, I like to imagine that there's like a mirror below you and they're like looking behind you, but whatever. So there's sort of 3 pictures I like to see RPN as. The first is this picture where you're living in 3-dimensional space. You're looking up, there's a copy of Rn above you. And if you look perfectly horizontally, then there's a copy of, it actually ends up being a copy of 1-dimensional lower projective space around you. The second picture I like is, instead of looking at each line intersecting the plane ones, you can see that each line should intersect the sphere exactly twice, which is at 2 antipodal points. And so a second way that you can describe it is you take the unit sphere and identify antipodal points. And so that's why you sort of have RPN minus 1 at infinity, because what you're doing is you're taking the sphere of 1 dimension lower, but you're identifying opposite points, right? So you have that, and the third picture I like is, I think the most down-to-earth picture when you're sort of doing problems with this, because RP2 is something which is actually 2-dimensional, because here it is some 3-dimensional thing, but after you scale, it becomes 2-dimensional again. And so what I like doing is like actually like a copy of R2 here with some circle at infinitely far away, where again you have to remember to identify opposite points. Questions on that? So again, what ends up happening here is like if you have a line in R2, then that ends up looking like a plane in R3, right? And so the statement that 2 lines intersect at a point become 2 planes always intersect at a line. And this is true even if the 2 lines end up being parallel. All that happens is the line of intersection between those 2 ends up being horizontal. So that exactly says that if you have 2 parallel lines, then they intersect infinitely far away. So these 2 parallel lines would intersect at this point at infinity. You can sort of work that out and see that actually does work like that. Questions on that? Okay, so let's look at some examples. So RP1, right? This is the unit circle with offset points identified. And what's the unit circle with offset points identified? So I'm considering like this point to be the same as this point, right? So let's like trace this out. Let's start over here. And so I'm gonna start over here.
Is it just the half circle?
Right, so if you like keep moving around, right, what you're gonna do is you're gonna trace this out perfectly until you get to this point. So what happens over here is like each of these points is unique. You haven't identified anything yet. Then once you get to this other end of the half circle, what happens is this point is the same as this point, right? So what ends up happening is like you actually have to sort of loop back on yourself. So what happens is like this is sort of the same circle, but like wound about itself twice. So RP1 is the same thing as S1. Okay. How about RP2? So here we're taking the sphere and we're identifying offset points. What should this be equal to?
Well, it's like the boundary of the hemisphere minus the interior.
Right, so it's the top hemisphere, and then the thing is on the boundary, you're like identifying things together,
Yeah.
right? And the thing is like you actually have to like twist this in such a weird way that you end up not being able to embed it into three-dimensional space. So the point is that RP2 is not equal to S2. In particular, it's something which is non-orientable. And I don't want to deal with orientations. So instead we're going to talk about complex projective space. Because Cohomology doesn't, it works in non-orientable manifolds, but it doesn't give you some things which you expect. So instead we'll work with complex projective space, which does. And complex projective space is defined in like the same way, where CPN equal to Cn plus 1 minus 0 modulo scaling. So again, now we have z1 to zn plus 1 is equivalent to lambda z1 lambda zn plus 1, where now lambda can be any complex number except 0. So this has all the niceness that it has all the intuitions of Rn, except that you can't actually visualize anything. So what happens is that this is like a 2n plus 2 dimensional space because C is 2 dimensional. Over R. And then you're removing 0, and then you're scaling by this guy, and because your scale factor has 2 degrees of freedom, you're removing 2 degrees of freedom. So this then becomes a 2n-dimensional space over R. So let's look at what CP1 looks like. CP1, okay, so RP1, right? So I said one of the pictures was a circle with object points identified. But I said another picture was you can look at a copy of R and then have like a point at infinity, right? And so what happens is like this point, you get an R with a point at infinity, which sort of like brings the two ends together and you get a circle. So does anyone have a guess as to what CP1 looks like? A sphere, yeah. So what ends up happening is you end up having a plane. And this is different from RP2 because RP2 you have a circle of points at infinity, but in CP2 what ends up happening is you have a single point at infinity. And so you have this whole outside of the plane gets collapsed to a single point, and what you end up with is CP1 is equal to S2. Okay? And CP2 is more complicated, it's some 4-dimensional manifold. But the point is that we want to understand CP2 because like Bézou's theorem, like I said, you want functions on the plane, but then, or polynomials in the plane. But I said you should go to complex numbers and work in projective space, so you should work in CP2. But CP2 is now 4-dimensional manifold, which is something complicated. So what I'll have you do is look at, in this response section of the problems, if you want to do it, to work out what the cohomology of CP2 and in general CPN is. And the one thing I'll say to that is I think the most useful viewpoint here is to imagine that you have, for example, for CP2, is that imagine you have a copy of C2 union with CP1, and this is sort of like the line at infinity. So this is some copy of S2, which is infinitely far away. So you sort of take your 4-dimensional complex space and somehow collapse it onto a 2-dimensional sphere in some strange way. And if you think about it like that, then you can try and figure out the cohomology of CP2. And I think in general, the way that I think of CPN is I don't try to visualize it at all. Try to imagine being an Rn, where I can at least imagine RP1 or RP2. You can also sort of imagine RP3 as like 3-dimensional space with like a sphere and right? And I try to take those intuitions into CPN and see how things work over there. So yeah, that's a little crash course on space of the day, CPN. Questions? Comments, concerns, why do we care? Yeah, so I think next week I'll prove Mayer-Vietoris, and then I'll start talking a little about intersections. And then when I talk about intersections, eventually one of the applications would be being able to prove Bayes' theorem. Yeah.
This is like a physics question.
Yeah.
So in like quantum mechanics, when you have a wave function, you don't care about global phases, and you assume they're normalized. And it seems like a lot like this complex projective space.
Yeah.
Is there?
Yeah, I mean one way to view quantum mechanics is that you're working in like projective space, and try looking at some videos online, and it's like some of the weird stuff that comes out of quantum mechanics, which they call anomalies, is like some sort of a failure. So like quantum mechanics should be some sort of projective theory where you mod out by scaling, so you don't actually care.
Yeah.
But then in order to do any sort of computations and stuff, you need to add stuff together, so you need to work with some vector space.
Yeah.
And sort of like the failure to be able to lift from like projective theory to a linear theory is like where some of the like strange stuff of quantum mechanics, which like you break some of like the classical symmetries, for example, and that breaking comes from like a failure of unity. So yeah, I think like this is sort of at some level important for if you want to understand quantum mechanics at a deeper level.
Thank you.
Cool.